Hello all, welcome to one more unit in the general undergraduate BTech course of engineering chemistry, that is phase rule. One of the important topic for those who deals with the equilibria of various systems, and it is said that the phase rule predicts the equilibrium existing between different phases of a heterogeneous system, and for that the phase rule is important. Now we'll see the phase rule in general is that credit goes to Willard Gibbs. In 1874-75 he came up with this famous phase rule, and it is a simple equation with very few terms, that is F is equal to C minus P plus 2, where F is degree of freedom, C is component, and P is phase. 2 is a constant, F is equal to C minus P plus 2. To know more about this equation, we have to first understand the meaning of each term, that is phase, component, and degree of freedom. We will go in this order, and then the definition. The standard definition is there, but you have to understand the terms first. The first term is the phase. When in general terms we talk about the phase, we understand what does it mean. Now let's put it in a scientific manner. Say for example, we talk about water is in vapor phase. That means water is in vapor phase. You know the conditions in which water exists in vapor phase. Certainly there is an increased temperature, and that is why the water is seen in vapor phase. If you open the door of the fridge and see that the door of the refrigerator and see that the water is converted to ice, you say that water is in ice form. So that is the phase. So all of the phases of various liquid, various chemical constituents can be expected, can be predicted based on the temperature and of course the pressure. So these two factors are there which are constantly in our mind while describing the phase of a system. We do not deal with pressure as such, because in normal course, in the household or domestic work and appliances, everything is dealt in terms of the temperature. Therefore we have less thought of pressure in our mind. All the processes around us are going on at atmospheric pressure, and that is constant, more or less for a geographical region, and therefore there is no much role of pressure that comes to our mind. But it is certainly there, and we have to take into account the pressure as one of the factors. Now say if we take an example of two liquids which are immiscible. Say in a test tube, I will draw the flat bottom, not the curved one. If the test tube has water plus benzene, say this is water and benzene, you will see that the two solutions are immiscible. They are not miscible. The two liquids do not mix in each other. But if you take another example of, say, water and ethanol, then you will find that the two are completely miscible, water and ethanol. When two are completely miscible, you will find that they cannot be distinguished, and thus this forms a miscible liquid pair. Thus, when two things are immiscible, the two liquids are immiscible, we call it that they exist in two different phases. When two liquids are miscible, then we call that they exist in one phase. You cannot distinguish between water and ethanol when they are mixed. And water and ethanol is miscible in all proportions. 1% ethanol, 99% water is miscible, and 99% ethanol and 1% water is miscible, and all combinations in between are miscible. You can see the simple example of the hand sanitizer that you are using. It is ethanol and water, approximately 70% ethanol. You know beer, you know the wines, whiskey, and all other uh, alcohols. They are all miscible. They are uh, say 48%, 40 to 48% of ethanol in rest of the water. So that is one phase. But if you take cooking oil and add it to water, you can see clearly the boundary between them, and thus they too are immiscible, and the two immiscible liquids form a boundary between them. And when such liquids or such compounds are separable by a definite boundary, then we call that they are in different phase. We will see certain other examples, like, say, two gases, H2 plus N2. Gases are miscible in all proportion in each other, and therefore they form one phase. Gases always form one phase. But if we take an example of calcium carbonate, which is solid, is converted to calcium oxide by heating, plus CO2 gas is given. In this particular equation, at equilibrium, you will find that there is one solid called calcium carbonate, there is another solid called calcium oxide, and one gas, that is CO2. In this case, the two solids are not miscible. No two solids are miscible unless it is a true solution like alloy. That is a different case. And therefore, when two solids are not miscible, then these two solids form separate phases, and the gas being one another phase. Thus, there are three phases in this equation, in this system. Two individual solid phases plus one gas. If you take an example of iron solid plus H2O in vapor form, that gives iron oxide in solid form plus hydrogen in gaseous form. Here Fe and FeO are two different solids, whereas H2O and H2 are two different gases. But as I told earlier that gases are miscible in each other in all proportion. Therefore, they form one phase. Therefore, here as well, the H2O and H2 will form one phase, but two solids will form two different phases. Though there are four different chemical constituents, but again, it will have three phases only. Two solid phases and one gaseous phase where H2O and H2 are present together. So thus the phases can be defined as an homogeneous, physically distinct and mechanically separable portion of the system which is separated from other such parts of the system by definite boundary surfaces. You can see that wherever the things are not visible, there is a definite boundary. For any two liquids, you can see that there is a definite boundary. If we take example of water and glucose, simply water and sugar. The sugar that is used in our day-to-day life. When you go on adding sugar in water, sugar goes into water and thus it is miscible. But at a certain point, when sugar solution becomes saturated, you will find that sugar is separated out. Sugar separates out at the bottom. If water and sugar are miscible, then it forms one phase. If there is some sugar left at the bottom because of the saturation being reached, then water plus sugar will form one phase and sugar solid at bottom will form one phase. Thus, there are two phases. So, if the solution is saturated, there are two phases. If the solution is not saturated, then there is only one phase. We can also think of the NaCl in water. NaCl is easily soluble in water. The salt, common salt in water, is soluble and thus it forms one phase. If you go on adding further NaCl, you will find that the solution becomes saturated, and in such case no more salt will go into water and thus that will settle down at the bottom and then it will form a different phase. Each solid makes up a separate phase and each gas is miscible with other gas in all proportions. Thus, these things decides how many phases will be there in a system and that you can observe closely. The next thing is the component. Simply speaking, component may be called as individual chemical constituent. To understand it at the simplest level, we can say that individual chemical constituent is component. So that is to begin with the understanding I am writing it like this, that a chemical constituent can be considered as a component. Say, if you consider the system where water is boiling, in such case H2O liquid is in equilibrium with H2O gases. When these two things are in equilibrium, when these two phases are in equilibrium, ultimately everything is H2O only, and thus it is a one component system. If you consider saturated solution of HCl in water, what will you see? Sorry, NaCl in water. You will see that when the solution saturates, solid NaCl separates out. And when solid NaCl separates out, then whatever NaCl is in water that has formed one phase, that is NaCl plus water, and whatever is saturated that goes at the bottom, that is NaCl solid. Thus, it has two phases and there is a definite boundary to separate them. Thus, everywhere the chemical constituents are not phases. You have to look for the homogeneity and definite boundaries. Also, merely because the temperature is changed or pressure is changed, if the chemical constituents are changing, then you have to look for the equations which represent the equilibrium between them. Say, for example, the example that we can consider is, one of the example is of ammonium chloride solid. If it is heated in a closed container, it is converted to ammonium chloride gases, and then it gets converted into ammonia gas plus HCl gas. Here you can see that as the container is closed, whatever ammonium chloride is dissociated, that gives equal mole of ammonia and HCl. Thus, at a particular instance, the concentration of ammonia is equal to concentration of HCl. That is one of the equation which explains the equilibria. Also, equilibrium constant can be given as the product of concentration of ammonia and HCl to the product of concentration of ammonium chloride. And as the active mass of solid can be neglected, ultimately K equilibrium is equal to product of concentration of ammonia and HCl. Thus, it is another equation which explains the equilibria. Now, in such case, there are two equations which explains the equilibria, and thus ultimate component are how many? There is only one component which is changing with pressure. and temperature. If you increase the temperature, it is dissociating into two, and if you increase the pressure and decrease the temperature, it gets back to ammonium chloride. That means chemically it is ammonium chloride only, and this can be defined as number of components are equal to the definition gives that number of components are equal to the the equations governing the equilibrium. And here, if total components are 3, total number of constituents minus number of chemical equations, number of equilibrium equations for this system. And here you can see that two equations are explaining the equilibria, and thus 3 minus 2, ultimately it is one component only. So the component is only changing because of the temperature and pressure, and thus it can be alternatively defined as the number of chemical constituents of the system minus the number of equations relating to these constituents in an equilibrium state. So if there is ammonium chloride plus HCl in the container, then ammonium chloride solid, HCl will be in gaseous form. In such case, if you heat the container, ammonium chloride will get converted into gas first, and then it will dissociate into ammonia gas plus HCl gas. Whatever HCl gas was already present in the container will get miscible in HCl itself. So chemically these are one species only. Thus, at a particular time, though equilibrium constant can be given as with this equation, but at no time concentration of ammonia will be equal to HCl, because always concentration of HCl will be higher than concentration of ammonia, because already HCl was present there. Thus, this equation cannot describe the equilibrium. In fact, this is the equation which is applicable, and only one equation which describes the equilibrium is the first one. And in such case, components is equal to total number of chemical constituents, those are 3, minus the equations describing the equilibrium, that is only 1, and the answer is 2. Thus in this case there are 2 chemical constituents, 2 components are always there. However you increase the pressure, if pressure is increased and temperature is decreased, then what will happen? These two, this and this, will merge to form ammonium chloride. Further cooled down, it will form ammonium chloride solid. But whatever excess HCl was there, that will be there. Thus, these two species, minimum 2 species, will always be there. There may be 3 species when this is in equilibrium, but minimum 2 species are required to define the system however pressure you increase. Therefore, two chemical constituents and two components are there. So this is the alternative definition of components. Now we will see the third factor, that is the degree of freedom. Degree of freedom is the freedom at your hand which you can use to keep the system in equilibrium. Say for example, if you are asked to operate a machine which is like a coffee machine which has three knobs. Say there is a simple machine, a chamber inside, and this is having the three knobs, just like a coffee machine. One knob is for volume, whatever solution, whatever liquid you have to add. Another knob is for adjusting the temperature, either decreasing or increasing, and one of the knob is for pressure. With rotation, this side or this side, you can rotate it and adjust. If this is the case, then if you are asked to operate all the three buttons, then you have freedom to operate three parameters. If you are asked that this button of volume should be locked, you are not allowed to touch it. Somebody has already added the water, coffee and milk in the container. You are only allowed to increase the temperature or decrease the temperature or increase and decrease the pressure. Then you have only two parameters in your hand. If somebody told you that you are not allowed to operate the temperature as well, this knob, then you have only one parameter. So this can be related as the degree of freedom. What is in your hand so that the coffee will be prepared? Ultimate goal is to prepare the coffee. That means ultimate goal is to bring that sugar and coffee powder into the water so that a colored solution with a particular taste that can be formed. So if you are asked to operate certain parameters so that you should get the desired outcome, then those parameters, either it is one parameter, either it is two parameters or three parameters, that can be called as the degree of freedom simplistically. Say for example, if you are asked to keep water at such a level where water liquid should be in equilibrium with water vapor. So H2O liquid should be in equilibrium with H2O gas. What will you do? You will heat it. If you give heat to water, that is converted to water vapor. But in the container, if you go on heating water, soon what will happen? All of the water will get converted into vapor. So you know that volume is getting evaporated. In such case, pressure is always at 1 atmosphere because you do not have any usual household mechanism to increase the pressure or decrease the pressure. But if pressure is at 1 atmosphere, that means pressure is fixed. If you have to keep this equilibrium, you know what temperature and what volume should be adjusted. So these things that are to be controlled are the degree of freedom. Simply, the degree of freedom is also called as variance, and it can be defined as the minimum number of independently variable factors such as temperature, pressure, and concentration or composition of the phases, which must be arbitrarily specified in order to represent perfectly the condition of a system. So you should know what pressure is to be defined and what temperature is to be defined if you have to establish the equilibria between H2O liquid to H2O gas. If you have to keep these water in two phases at equilibrium, you should know the temperature and pressure which is required to be maintained if composition is constant. Say 1 liter water is given and that is fixed. In a closed container, in a closed cooker, no water is going to evaporate, then it is in your hand what temperature and what pressure you should keep so that the two phases will be in equilibrium. If you cool down the entire system at 1 atmosphere, it will be converting into only one phase. So like that, all of the degree of freedom are nothing but the three parameters: temperature, pressure and composition, which you have to handle so as to keep the system in desired equilibrium. We will see what does it mean exactly with the help of the phase diagram of water in our coming lecture. Thank you.